welcome to the second lesson for vertical projectile. In this lesson, we are going to focus on the graphs. Vertical projectile graphs. We are going to focus on vertical projectile graph. Without wasting any time, we'll get straight to the business. The vertical projectile have got three types of graph. The first graph, which is the most common one, it is what we call the velocity time graph. The first graph, which is a common graph, is the velocity versus time graph. We call velocity time graph. Then we have what we call the position time graph. The position time graph. Then the last graph, we're going to have the gravitational acceleration. This is time graph. So we are going to touch on three graphs, namely the velocity versus time graph, the position time graph, and the gravitational acceleration time graph. Today is the 13th of October. You are left with very few days for you to write paper 1. Next month, November on the 10th, you are writing paper 1, Physical Sciences 2023. This video is taken in 2023. I know some of them will watch it in 2024, 2025. Vertical projectile. We are going to start. We're going to start from there. Background information. In lesson 1, I was teaching content. If you haven't watched lesson 1, check lesson 1 so that you have a broader understanding. I'm going to start from background information number 1. Number 1. We've already defined a projectile. We said that a projectile is an object which has been given initial velocity and it moves under the influence of gravitational force only. You must not forget the word only, because a projectile, it's an object which has been given initial velocity and it moves under the influence of gravitational force only. So, as this object falls, it's a projectile. The only force acting is gravitational force only. So, number 1, background information. When an object moves up, its velocity decreases. As the object is moving up, its velocity is going to decrease. It's very important for us to understand that, because when we draw the graphs, we will make the drawing which will communicate with these statements that I'm giving you. So, when an object is moving up, its velocity is going to decrease. Here I'm holding an object. As this object moves up, its velocity decreases until at the maximum position, the velocity becomes 0. We know that if I have an object on the ground here and I project the object up, the object is going to move up, but its velocity is decreasing, then it will come down. Let's say it will return to its position. We know that the velocity at maximum height is going to become 0 meters per second at maximum height. It means that as the object moves up, the velocity of that object is decreasing as I wrote. So statement number 2, when an object moves down, its velocity increases. So it means that as this side the object is moving up, the velocity will be decreasing. But when the object starts to move down, velocity will increase. So when an object is moving down, its velocity is going to increase. The velocity that is at this position will not be equal to the velocity that is at this position. So when an object moves down, its velocity decreases. When an object moves up, its velocity decreases. I'm sorry about what I say. When an object moves down, velocity increases. When an object moves up, velocity decreases. Sorry about what I said. These two important statements. Our graph is going to start from the two important statements. Okay, let us start from the velocity versus time graph. Velocity versus time graph. So the velocity versus time graph, the Cartesian plane for the velocity versus time graph is like this. Then we have the y-axis and the x-axis. We know that the time is an independent variable. Time does not depend on anything, so time is going to be plotted in the x-axis. And the time is in second. Then on the y-axis we have got the dependent variable, which is the velocity. And it is in meters per second. So whenever you draw the velocity time graph, you need to clearly indicate this axis. You need to write that the y-axis has got the velocity in meters per second, the x-axis has got time in seconds. So this is the Cartesian plane for velocity versus time graph. So now I can talk about a scenario, then we will be drawing different graphs based on different scenarios that I will be giving. You can see that this graph has got the positive y-axis and the negative y-axis. You know that here we have got negative value and values, and here we have positive values. So what does that mean? It means that if we want to take downward as negative, it means this part will be representing downward. And then upward will be represented by the positive x-axis. So I can say downward motion. This is downward, this is upwards motion. Downwards or upward motion, or vice versa. This can be upward or downward motion. So notice that these two parts, one part represents when an object is moving up. And if I take this one as up, it means this one will be down. So you need to take note that we have got the positive y-axis and the negative y-axis, whereby each represent upward and the other represent downward motion. You need to take note of that. Okay. So now, what I would love to notify you about is that it does not mean that if you draw a line that is going down like this, it does not mean you are representing an object that is going down on velocity versus time graph. It doesn't mean if somewhere I happen to draw a line that is moving up like this, it does not mean that I'm saying an object is going up. So this is not a position time graph. The manner in which you can draw the lines does not represent anything. does not represent anything about the lines. So now we can start. Let's say I do what? A man is standing. Okay. There are words which I want us to look at so that we can be equipped to deal with this velocity versus time graph. Sometimes you will find words like the object is projected. The object is projected. Whenever you hear the word projected, when you project something, you see, I'm holding two objects. When you project something, it means you are going to give that thing an initial velocity which is not zero. If I can throw things, throw this object, I throw it. Its velocity, the initial velocity, it was not zero. Look at it. If I throw that object, you saw the object was coming towards you. Or if I throw this one, you saw the object was coming towards you. I projected that object. Its initial velocity is not zero because it was projected. So the word projected, it means that the initial velocity of an object that is projected is not zero. It's not zero, the initial velocity. But sometimes we come across the word dropped. You hear that? A ball was dropped. When you hear statements like something is dropped, look, I'm holding something here. If I drop this, it's like I'm holding it there, I let go. If I let go, the initial velocity of this object, it cannot be a 1 or 2 or any number greater than 0 or a negative number. No, it is going to be 0. Look at it. The object is still, it's not moving, it's stationary. Then I let go. When I let go, I've dropped it. It means that the initial velocity of this object is 0. Why is it 0? Because the object was dropped. So you're going to hear that an object was dropped or the object was projected. Sometimes you will hear statement that something is released. Something is released. If something is released, it's like, you see, I'm having an object here. I'm having a book and an object. You see, this object, it is stationary now. Then I let go. When I let go, it will start to move. That is releasing. You see, it is stationary. Then I let go. It means I've released it. It means that its initial velocity is 0. It means that the initial velocity of this object is 0. So when you drop something or you release something, the initial velocity is 0. So those are the keywords which we need to understand. So now we can start to deal with a real scenario. One thing that you need to remember is that when an object is moving up, its velocity is going to become 0. When an object is moving up, its velocity at the maximum height it will become 0. Meaning that when an object moves up, velocity decreases. It means if you are told that an object is moving up, it means you need to make sure that your graph will be approaching 0. Where is 0? 0 is here. This is a normal Cartesian plane that we know. It's just that we cannot draw a path which we do not want to use. You see, this is x0, this is 1, 2, 3, 4, this is negative 1, 2, 3, 4, this is positive 1, 2, 3, 4, this is negative 1, 2, 3, 4. You understand? Meaning that we don't want to use this part, we only want this part. So we erase this part. You know that's what we do in graphs, in mathematics. Then this one is our 0. So notice that this is the normal Cartesian plane that we know from mathematics, is that we eliminated this other part, so this is 0. So what am I saying? I'm saying that as the object is moving up, what will happen? As this object is moving up, its velocity as it moves up is decreasing. That's why it will get to a position where its velocity becomes 0, then it comes down. So, if you are representing an object that is moving up, just know that your line must be approaching 0. It must be moving towards 0 because the object is moving up. But if an object is moving down, it means that its velocity is increasing. When an object is moving down, its velocity is going to do what? To increase, meaning that when you draw a line, that line must be moving away from 0. You understood that? Okay, maybe let me do it in writing. If an object is moving up, the graph must approach 0. Why is it approaching 0? Because as an object is moving up, its velocity is decreasing, meaning that it will be approaching 0. Number 1. Number 2, if an object is moving down, if an object is moving down, the graph must move away from 0. Meaning that whenever you are representing an object that is moving down, as the object is moving down, it means that the graph must be moving away from 0. It's either it is moving away from this side or it is moving away from that side. Because the object will be doing what? Will be moving down. So as the object is moving down, its velocity is going to decrease. So I can just add the third statement. At maximum height, the graph must touch the x-axis. At maximum height, the graph must touch the x-axis. When you say this is maximum height is on this line. You see? On this line, that's where everything is 0. Meaning that at maximum height, your graph must touch this line. Understand? At maximum height, your graph must touch that line. So these are statements that I'm giving you. They are the foundation for you to understand the graphs, vertical projectile graph, velocity versus time graph. Okay, let me start from something that is simple, whereby you are having only one ball, only one object. Okay, let me show that to you. I told you that we must always write our axis time in second. This is 0.0. You need to indicate this is velocity, this is time in meters per second. So, okay, let's say where we have this. Let me give you the scenario. Here's the scenario. This is the ground. This is the ground. A ball is projected up. Then the ball comes back to the same position. Can you see? The ball is projected up and it comes back to the same position. It's just that here I did not draw the axis. This is a position time graph. Whenever you see me representing a ball like this is a position time graph. But since this is not a graph because it doesn't have axis, you will see after showing you this graph when I show you position time graph. But this is a position time graph. So here is the situation. A ball is projected up. When something is projected, it means that it is given initial velocity which is not zero. So let's say we say a ball is projected up at 4 meters per second. The ball is projected up at 4 meters per second. Then it takes 0.3 seconds to reach its maximum height. Okay? A ball is projected up at 4 meters per second and it takes only 0.3 seconds to reach its maximum height. So, from the information that was given, let us use the theory that I taught you in lesson number 1. How do we solve it? It means that since this object was projected from this point, let me label this point A, point B, point C. Since the object was projected from point A, then it came back to point C, which is an equal position or same level as point A. What does it mean? It means that since it went up and its initial velocity was 4 meters per second, it means even coming back from point C, because it is the same position, you can see they are on the same level, they are the same. If from point A to point B is 2 meters, it means even from point B to point C, it is 2 meters because the same position. So, since a ball was projected up and it came back to the same position, it means that even the final velocity at which it will hit this point C at, it will be 4 meters per second. Although that was not given, but we use theory that we know. So it means the ball is going to come back to this point C and it will be moving at 4 meters per second. At point B, the maximum height, what is the velocity? Velocity is going to be 0 meters per second. I can label, I can say this is 0 meters per second. At the maximum height, this is 4 meters per second. How do we know? It's because we are told that the ball was projected up at 4 meters per second. So since from point A to point B, it took 0.3 seconds. 0.3 seconds. It also means that going down, coming from B to C, which is the same position, it will also take 0.3 seconds. 0.3 seconds. So we want to represent this scenario on this graph. How do we do that? Let me make you capture the question, since I'll be giving this question so that I draw different scenarios. I will not be coming up with a question from a question paper. I'll do that later because now I'm still teaching you. I must give you many different scenarios so that we represent them on this velocity versus time graph. Okay, so now we are told that an object is projected up at 4 meters per second. It reached its maximum height. It took 0.3 seconds to reach its maximum height. Okay, so let us draw that on the graph. I told you that the maximum height, since the velocity is 0, it must touch this line, the x-axis. The maximum height is the x-intercept. Okay, so let us draw that. We are taking up as positive. You can see. We are taking up as positive. Meaning this is 1, this is 2, this is 3, this will be 4. The same thing is going to happen. This is going to be -1, -2, -3, -4. Most of the time they do not write these spaces. But make sure that 1 and 1, they've got equal space. 2 and negative 2, they've got equal space. Negative 3 and they've got equal space. Because these spaces, this graph, have got a meaning. Okay? So let us do that. We have taken going up as positive. So, look what is going to happen. The object is going up and it reached its maximum height. Right? It's going up to reach its maximum height and it took 0.3 seconds. So, going up, we're taking it as positive. Its initial velocity was what? It was 4. It started at what? At 4. And the object is going up. Remember, when an object is going up, its velocity will be what? Will be decreasing until it becomes 0. So, going up, we take it as positive. So, what will happen as the object is going up? Its velocity is going to do what? To decrease. That's why its velocity, it will start as 4. It decreases, it becomes 3.9. It becomes 3. It becomes 2.9. It becomes 2. It becomes 1.5. It becomes 0.5. Then it becomes 0. You understand? So as the object is moving up, its velocity is decreasing. That's why this is velocity. These numbers represent velocity. So as the object is moving up, its velocity is doing what? Is decreasing. I hope you are understanding. As the object is moving up, its velocity is decreasing. That's why you see the velocity being decreasing here. Then, until it's reached its maximum height. Its maximum height, here, the velocity is what? Is 0. That's why you see a 0 there. You understand? Then, we move up. We go to the second part, when the ball is coming down. You see, when the ball is coming down, there is a statement that I just told you that if an object is moving down, it means that its velocity is going to increase. As the object moves down, the velocity is going to increase. That's why it means the velocity will start from 0 here. Then it will become 1. Then it will become 2. Then it will become 3. Then it becomes 4. You understand? So here the velocity is going to be 4, 3, 2, 1, 0. Then here it will become 0, 1, 2, 3, then 4. You can see that these velocities are corresponding. If when an object was going up, if at this position it is 3 meters per second, when it is coming down at the same position, it will be 3 meters per second. You understand? That's what I'm saying. When an object is going up, velocity decrease. When it is coming down, velocity increase. So as the object comes down, what will happen? The velocity is going to what? Is going to increase. That's why you see the velocity. As the object is coming down, the velocity does what? Increase. Then as it will reach its destination and it will be at 4 meters a second. You can see that this line and this line are the same because the velocities are the same. Okay? We are left with plotting the time. You see at maximum height, this is a maximum height. Why am I saying it's a maximum height? It's because at maximum height, velocity is 0. It means this is the maximum height and velocity is 0. So how many seconds did it take? It traveled this second. It took 0.3 seconds to reach its maximum height. I hope you are understanding. It took 0.3 seconds to reach its maximum height. It took 0.3 seconds to reach the maximum height. It took only 0.3 seconds to reach the maximum height. What about coming back? If it took 0.3 going up, even coming down, it will take 0.3. So it will mean from 0 to the maximum height, it took 0.3. Then to come down, it will take another 0.3. It means here is 0.3 plus another 0.3 of coming down, which will become 0.6. So it means to go up and come back to its original position, it will take 0.6. So this will be 0.6. So this is the velocity, this is time graph of an object that is moving up and it comes back to its original position. I hope you understand. I hope you understood what I just did. Okay, if you haven't subscribed, don't forget, subscribe. Support this channel so that we can keep on doing videos. Share these videos. We want people to know about this program because this program is assisting many kids and are improving their results. Okay, I want to give you another scenario. Let me erase this one. I'm erasing this one. Let us come up with another scenario. Remember, when an object is going up, velocity decreases. When an object is coming down, velocity increases. Okay. Okay, let me give you a scenario. Here it is. A person is standing at the top of a building. This is a building, a very nice triple story. A very nice triple story. Okay, these are windows. Then the person is standing here. Then the person projects an object up. Then the object comes and hits the ground. You see? The person projected an object up and then the object hits the ground. I want you to draw a velocity versus time graph for this scenario. The person projects an object. Notice that this object was projected. This object was projected. So this object, it moves at not 0 meters, but it is projected at a particular velocity, then it moves up, then it comes down and hit the ground. It is not coming at the same position. So let me say this object was projected at 3 meters per second. The object is projected up at 3 meters per second. And it took 0.2 seconds. Take 0.2 seconds to reach its maximum height. Maximum height. I'm writing this thing so that I teach a lot of scenarios, then we'll do a question which I'm going to paste there, then work it out together and we'll get the answer. So an object is projected up at 3 meters per second and it took 0.2 seconds to reach its maximum height. We're good, right? It took 0.2 seconds to reach its maximum height. So we want to draw that. We want to represent that on the graph. We want to represent that on the graph. How can we represent that? There is a lack of information. There is a lack of information. We don't have enough information, but we're going to draw the graph, the correct shape. Okay, so what do we know? What we know is that the velocity that is here, it will be the same as the velocity that will be in the same position, you understand? Even here, it is going to be 3 meters per second. Notice I never said here. I'm saying here. Why am I saying here? Because it is the same position. It is the same position. Here, at maximum height, it will be 0 meters per second. At same position, here, it will also be 3 because the velocities of an object, when it returns to the same height, it will be the same as the initial height. You understand from lesson number 1. So if it took 0.2 going up, even coming down, and reach this point, only this, we don't know about from this point to this point. So here it will take 0.3. Understand? So we need to represent that. We do not know the final velocity and we don't know the time here. We can calculate it, but now I want us to represent that on the graph. So we are in short of values. But we can be able to draw it. This is how we draw it. We're going to have the what? The Cartesian plane. This is 0. This is velocity in meters per second. This is the time in second. Right? Then the object is projected up and it moves at 3 meters per second. It moves up and it took 0.2 seconds. So here we're going to, we can say this is 1, this is 2, this is 3. Can you see? This is -1, -2, -3. Can plot as many points as we can. Okay, let us plot that. So this will be at 3. You see? At 3. The object is moving up. As the object is moving up, what is happening to velocity? As the object is moving up, velocity is decreasing. So, as the object there is moving up, velocity is decreasing. That's what I said when I started to show you the graph, that as the object is moving up, its velocity will be approaching 0. Can you see that as the object is going up, this graph is approaching what? 0. So as the object is moving up, velocity is approaching 0. It is slowly becoming 0 until it becomes 0 at the maximum height. It started at 3 meters per second. As it moves up, the velocity is doing what? Is decreasing. So here we are going to have 0 meters per second at maximum height. And how many seconds did it take for this ball or this object to reach its maximum height? It took 0.2 seconds. Yeah, it took 0.2. If I happen to say 0.3 initially, it was a mistake. You can see I said the 0.2. So since going up will take 0.2, if you're coming down, you take 0.2. So it took 0.2. Then let us see. Then that object moved. I want to show you something. I don't want to write this. What is happening here? At this point, what is happening at this point? For example, when the object is going up, this represents going up, then coming down and reach this position, it will be at 0.4. This is 0.4. Why is that 0.4? Because if going up it took 0.2, even coming down to the same position, it will take 0.2. But for this question, it didn't just stop here. The object continued to move. So here, at this point, is 0.3. But we know that as the object is moving down, the velocity is going to increase. So we are going to extend this line. We are going to extend the line. We are not going to plot anything here. And even the time, we are not going to plot anything. Why are we not plotting anything? That is because we are not given the final velocity that is here. And we are not given the time from this point to this point. So we're just going to draw a line which is longer than this side. Why is this line longer than this side? It's because we know that the velocity, final velocity when the object is coming down will be greater than the velocity when the object was moving up. Why? As the object is coming down, it will be what? Its velocity will be increasing. That's why the velocity of here it is 3. It means as the object is moved down, the velocity will be increasing. We'll be saying 4, 5, 6, 7, 8, 9, 10, blah blah blah. We don't know the final velocity here, but we know that the final velocity that is here is greater than 3. So that's how we can represent that scenario. I hope you understood. Okay. We can further say that I want us to let's say we are given the information this time around. I'm furthering that question. Let's say we are given the information. I said that the final velocity here, is 7 meters per second. Is 7 meters per second. The final velocity is 7 meters per second. I say it took 0.8. It took 0.8 seconds to reach ground. It took 0.8 seconds to reach ground from maximum height. What does it mean if it took 0.8 seconds to reach the ground from maximum height? What does it mean? It means that the final velocity we are given is 7. It means this will be 1, 2, 3, 4, 5, 6, 7. Can you see? It means this will be 0.7. This is 7 meters per second. 7 meters per second. 7 meters per second. Now we want to know the time. They are saying that it took what? 0.8 seconds. Notice there is no way where I'll be writing 0.8 seconds here. It means from this point to this point it's 0.2. This point to this point 0.2 again. Or from this point to this point 0.8. Because they said that the object took 0.8 when we are going down, it does not mean that I will write 0.8. Remember, time is moving, like there will be no way whereby time will stop. Time will keep on moving, meaning that whenever they say it took 0.2 going up, coming down it took 0.5. It means you are going to say 0.2 plus 0.5 as you plot here. So, what do we say? It means we're going to say 0.2 plus 0.8, which will become 1 second. You understand? So it means this will become 1. This is 8.1. Understand why is it 1? Because they are saying that from this point to this point, from this ground to maximum height, it took 0.2 seconds. Then to reach this ground of the building, it took 0.8. So it means we're going to say 0.2 plus 0.8, then it will become 1. So it means this is 1. And you can see that this side is longer than this side. Why? It's because we know that as the object is moving down, velocity will be increasing. Okay, that is another scenario. The velocity, this is time graph. Velocity, this is time graph. Okay. Let us talk about a situation whereby an object is not moving up and down. An object is projected down. How do we represent that scenario where an object is projected down? How do we represent that scenario? Okay. Let me say someone is standing at the top of a very nice double story. This one is a double story, guys. This is a graph, it's a double story. The person is standing here. Then the person dropped a stone. The person dropped a stone. The person dropped a stone. The stone is dropped. Remember, when something is dropped, its initial velocity will become 0. So someone just dropped a stone. When you drop a stone, the initial velocity of that particular thing is going to be 0. Then the stone hits the ground. The stone hits the ground at 6 meters per second. Someone dropped a stone. To drop, just let go. and that particular thing start to move. So since I told you initially that the word drop, it means the initial velocity of the object is going to be 0. So since the stone is dropped, it means that its initial velocity is going to be 0. So we're going to start from 0. But since the object is moving down, what will happen to the velocity? The velocity will be increasing. Because when an object is moving down, velocity increasing. So let us represent that on a velocity visit time graph. Velocity visit time graph. Going to have that. We're going to have time in second. Then we're going to have velocity in meters per second. This is at 0. It means the object was dropped. I mean, a person dropped a stone. I'm thinking that I should have drawn two types of graphs for both the examples that have been given, depending on how your teacher is teaching. Note guys, if you understand what your teacher is doing and I come with my new method, time is gone. Don't try to want to change a method. Stick to that method. Just add the information from some of the things that I'm saying. Unless if you were not taught this or you were not taught well, you do not understand, that's then you can take everything that I'm saying. Okay, let us represent that a stone is dropped and it hit the ground at 6 meters per second. It means its initial velocity is going to be 0. The velocity will be increasing. It means that since the stone is dropped, this will become 1, 2, 3, 4, 5, 6. See that? See that? Let's say the stone took 0.6 seconds to reach the ground. So if the stone took 0.6 seconds, it means it's going to start from 0. Remember, it is being dropped, meaning that its initial velocity is 0. Then it moves down. It moves down. So notice that I'm drawing a line which is moving like that. Why is my line moving like that? The line is moving like that because I took down as positive. Yeah, I took down as positive. That's why I'm drawing downwards here. I will draw another graph which represents the same thing. So it means here is at 6. Then here, what will happen here? What will happen here? Then it took 0.6 seconds. So you can see the object is dropped. Then it hit the ground at 6 meters per second. So its initial velocity will be 0, and then its final velocity will be 6. You can see it, right? So as the object is moving down, velocity is increasing. Can you see that? As the object is moving down, velocity is increasing. Understand, right? Okay, let me draw the same graph here using another method. Not necessarily another method. Changing sign, right? Meters per second. Then this is time. This is time. Time in second. Then the velocity or the initial velocity of that object is 0. Then the object will move down. As the object moves down, it means you can represent that like this. I took down as a what? I took down as a negative. So I'm going to have 6 meters per second. Then here it took 0.6 seconds. You understood? This graph and this graph, they represent the same thing. It's just that on this one, I took down as a negative. That's why you see an object moving down. I just took down as a negative. Here I took down as a positive. These two, they represent the same thing. So that's what I was saying when I paused, that I must draw two graphs so that you understand and you choose the one that you want. So this is a velocity versus time graph of an object which is projected, which is dropped. It's not projected, it's dropped. Okay, so let us have a situation where an object is projected. Let us have, let me change this question. This is a person who projected. The person projected a stone downwards at 2 meters per second. You see, the initial velocity of this stone will never become zero because the stone was what? Was projected. So since the stone was projected at 2 meters per second and it took 0.2 seconds to reach ground. The stone, let me check, I'm doing the same thing, but I'm changing the way, the phrases, so that you can understand. The stone hits the ground. The stone hits the ground at what? At 10 meters per second. Draw a velocity visit time for that. So if I want to draw a velocity visit time for that, I'm just going to start by what? Drawing the Cartesian plane. Then I have time. The time is in second. The time is what? In second. Then I have the velocity. I have the velocity. The velocity is in meters per second. I have the velocity in meters per second. Velocity in meters per second. Then I have the time. This is the Cartesian plane. Then what do I do? Let me represent that. The object is projected down. The object is projected down. The object is projected down. A person projected a stone down was at 2 meters per second. It means the initial velocity of that object is 2 meters per second, but it is moving what? Down. So how do we represent that? I'm taking down as positive in this first graph. I'm going to take down as positive. So if I take down as positive, it means that the initial velocity of this object is going to be 2. So this is going to be 1, then this will become 2 meters per second. Then, since this object was projected down at 2 meters per second, it means its initial velocity is what? Is 0, meaning that this object is going to start from 2. The object is going to start from 2, then it moves up until it reaches what? 2. The final velocity is 10. 10 will reach 10. The final velocity is 10, so it's 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is this one. 10 is this one. Meaning that it has reached 10. This is going to be 10 meters per second. Listen, these spaces that you leave here, they must be equal. You don't just decide that this is a 10, this is a 3. No. The spaces must be equal because this line must talk something. This line must talk something. Then it took how many seconds to reach the ground? It took 0.2 seconds. So this is going to be 0.2. So you can see that I've changed the equation. That time the object was drawn. This time the object was projected, meaning the initial velocity changed. The initial velocity this time is 2, meaning I'm going to start from 2. You understand? Okay. If I want to take downwards, I will not draw it here. I know that if I can draw it here, you're going to draw your own new things to your teacher. So this is the graph. So if I want to take what? Downwards as negative, this is what I'm going to have. Here is velocity. This is velocity there. This is time. This is time in second. So if I want to take downwards as negative, I'm going to say the velocity is going to start, the initial velocity is negative 2. Since it's negative 2, then what will happen? The object will move like this, and its velocity is going to do what? To increase. Then I'm going to have that, I'm going to have that. Going to have that. This will be at 10 meters per second, the final velocity. Then it took 0.2 seconds to reach this another. So this and this is the same thing. Can you see that it's just taking this graph and you take it to become like this, to look like this. These are the same thing, same scenario, same situation, same thing. Okay, so that's how we draw a velocity time graph. Velocity time graph. Okay. Let me go to the part which is usually difficult for most of the kids. The part which is usually difficult for most of the kids, I'm going to talk about a ball that is bouncing. Velocity versus time graph for a ball that is bouncing. Okay. Okay, let me give you a scenario. Let's take a ball. The ball is projected up, move up, then the ball does what? It bounces and return back to them, and return back up, and then comes back. Right? This is a scenario. The ball is projected up, then it came down, it bounced, and returned back. Listen, to bounce is when you return back, it's when you say bounce and return back. To bounce is to return back. So do not confuse. You know that since English is not it's a language of learning for us only. At home we don't speak English. So we make a mistake that because of language barriers. So bouncing is when the ball moves up again for the second time. That is bouncing. So don't confuse bouncing with something else. To bounce is not to touch the ground. To bounce is when it returns up, when it is up again. To bounce is not just to touch the ground. It's to return up. Okay. So here is a scenario. Then the ball was projected up, it went up, then it bounced, then came back down. So, sometimes they will ask me a question that why does the ball, why is it that the ball is unable to return to the original height like this? So, when you take a ball and you make it bounce, you need to understand that the ball is going to produce sound, and that sound is going to cause the ball to lose some of its energy. So it will not have enough energy to return to its original height. And when the ball touches the ground because of friction, some of the energy will be converted to heat. It will be converted to heat. Then it will be lost and get converted to heat. So the ball will lose some of energy in the form of sound or heat, and it will fail to return to its original position. So here is the scenario. We want to draw a velocity versus time graph for this scenario. This ball is projected up at 6 meters per second. 6 meters per second. It projected up, then it bounced. It bounced back, and when it bounced back, it will be at 3 meters per second. It takes 0.8 seconds for the first time. When it returned up again, it just took 0.3 seconds. It took 0.3 seconds to go up when it rebounds, going up again for the second time. We want to draw a velocity versus time graph for this scenario. Let us plot what we know. This ball, it was projected up, then it returned to the same height. We know that when an object returns to the same height, it means when it hits the ground at the same height, it will still be having 6 meters per second. We know that from theory, lesson number 1. So it means the ball here, even here, it will be 6 meters per second. This 3 is when it goes up again. So at the maximum height is 0 meters per second. If we talk 0.8 going up, even coming down to same position, it will take 0.8. If we took 0.3 second going up, when it comes back returning to same position, it will take 0.3 again. At the maximum height, it is going to be 0 meters per second. So let us draw a velocity time graph for that scenario. I'm going to divide this scenario into 2. You can see there is a space in between the 2. I'm going to draw the one which has got the space between the 2 and the one without the space between the 2. So let us draw a velocity versus time graph for that one. So you know we're going to have the Cartesian plane. We have the velocity, then we have meters per second, then we have time in second. We must never ever forget to plot these axes correctly. Then we start with the first situation. The first situation. You know that as the ball is moving up, the graph must be approaching 0, because as the ball moves up, the velocity decreases. So as it decreases, it will be approaching 0. So let us draw that. This ball, it was projected at 6 meters per second. So we're going to say this is 6 meters per second. Then 6 meters per second. Then what will happen? Then 6 meters per second will be here. This side and this side, they must be equal. This 6 and this 6 must be in the same position. They must be equal, so that the graph can talk correct information. So it was projected up at 6 meters per second. Remember, as the object is moving up, the velocity will be doing what? The velocity will be decreasing, then until it reaches 0. You can see the velocity here is 0, it is at the maximum height. Then it returns back, the velocity starts to increase, it will start to say 0, 1, 2, 3, 4, 5, 6, until it reaches 6. Understood? Then? Okay. So this is the first scenario. Okay. This is the first scenario. Let me erase this. I will do that after. So at the maximum height, how many seconds did it take from the start to the maximum height? It took 0.8. Then to return to its position. This is not very much straight, guys. We must draw straight thing. I usually fight with kids when they do not draw straight thing. Let me also draw something that is straight. At least it's straight, because I'm not using a ruler. Yourself, you must use a ruler all the time, so that you draw proper things. Then here we'll have, this is going to be 0.8 plus 0.8. So it means it is 0.8 plus 0.8, it is going to be going to add 2, then we're going to have 1.6. So here it will be 1.6 seconds. It will return to its original position. Okay. Then look at it. There is a space between the two. You see, this space is what we call contact time. Contact time, yeah. Let me also try to expound more on this. Whenever you see a position time graph which is like this, and there is a space between this represents contact time. Contact time. What is contact time? This is the time an object was in contact with the ground. You know that if I throw this, it will touch the ground and leave if it is bouncing. It touches the ground and leave if it is bouncing. So it means this is the time where the object was touching the ground. Because there is no way an object can just touch the ground and move immediately. It is going to spend some few seconds, very small second, once it is touching the ground, then it bounces back. You understand? So the space between this, there's a space here. It represents the contact time. So how do you represent that? So if you want to draw two graphs, this is what you do. I usually tell my kids that this is the x-axis, right? It's like when you draw the first one, you take, this is the y-axis, not the x-axis. When you draw the first graph, you take this y-axis, you move it and you come and put it here. Then you start to draw another one while you are having a new y-axis. Understand? Well, this y-axis, I am done with drawing the first one. I take my y-axis, I put it here, then I draw the second one with the new y-axis. So you move this y-axis of yours, you come and put it where the other graph ends. You can see that already there is a line which represents the time. So I continue that line like this. What did I do? I have created another y-axis. Can you see that? I created another y-axis. You can see that this is the y-axis. It is the new y-axis for the second bound. So I can say that I took my y-axis, I came and put it here. Then I will draw the second graph. If the ball was bouncing again for the second time, I'm taking my y-axis, I put here, I draw the second graph. The same thing happened. I take my y-axis, I put here, I draw the third graph. You understand? So now I have a new y-axis, but there is what? There is a space here. Can you see that space? There's a space here. You understand? There is a space. I should have written the contact time, but I will do it in the second example. So, since there is a space, it means if in yourself you must leave a small space. The reason I'm saying you must leave a small space, I did not give numbers here. If I should have given numbers, the space was going to be reflected by the time. So I did not give the contact time. So it means you just leave a space. You won't start your graph here. Why are you not starting your graph here? Because there is contact time. This time. You understand? So if this graph was like this, you see, there's no space between the two. We're going to start from this line and you draw the second graph. But because this time around there is a space, you need to also make a space. So the initial velocity there is 3. So where is 3? 3 is somewhere here. So here is 3. This is 3 meters per second, which will be here, right? Then it moves up. As it moves up, velocity decreases. It decreases, it reaches maximum height. At maximum height, velocity is 0. Then it comes back to minus 3. So minus 3, here it is. And here is minus 3. I did not leave space. So we must leave spaces because there is contact time. I said something and I never did it. So it means your graph must start here. Why is it starting here? Because there is contact time. Then it becomes like that. Understand? Why am I leaving space here? Because there is a space here. If there was no space, I should have started it on that line. I hope you understood. So this is 3. Can you see? This is 3. This is 3. Then it reaches its maximum height at 0.3 seconds. So this will become 0.3 seconds. No, it will never become 0.3 seconds. Remember, it is the second bounce. I hope I did not confuse you. It is when the ball bounces, first bounce I mean. It is when the ball bounces. It took 0.3 to reach its maximum height. Meaning that, remember, from the start until the end, there was no point where time stopped. Isn't it? They were using a stopwatch, so time was still being counted. So you're going to say 6 plus what? Plus 0.3. Although there's going to be a problem because I did not include the contact time. We should have included the contact time, then we add the contact time plus 0.3. So since we did not do that, we have the right to say 6 plus 0.3. I mean 1.6. This is not 6. 1.6. This is the 1.6 then plus 0.3, which will become what? 1,6 plus 0,6789, it will become 0,9. It means it reached its maximum height after 0,9 seconds. Then 0,9 plus 0,3, which is going to become 2 seconds. No, 0,9, 1,9. What's wrong? You might tire. 1,9, then plus 2, it is going to become, plus 2 is going to become 1,1. So this is going to be 1,1. So this is how we draw a graph with the bounce. I murmured a lot when I was giving this example. Let me do another one so that I can flow. Okay? Let me erase this one and I give you another one. Just the last one. Just the last one when an object is bouncing. When an object is bouncing. Okay. Sometimes you will be given a position time graph. That I haven't started to teach the position time graph. I just want to make you understand this. They say this is obvious is time 0, then this is 0,5, this is 0,7, this is 0,7, then this is 0,9. That is 0,9. Understand, right? So yeah, here it is. Let's say you are given this. This is a position time graph, right? Just that I won't write the axis here. I'm teaching you velocity versus time graph for now. So I just want to explain this because sometimes they will ask you questions whereby you need to explain this. You see this space in between is the contact time. This is the time where the ball touches the ground. This is the time where the ball touches the ground. If I happen to project the ball is going to touch the ground, then it will return to the air. It touches the ground. So this is the time when the ball was attached to the ground. So if they can ask you, what is the contact time? The contact time is this time. The contact time is this time. It means the ball touched the ground for this time. It means the contact time is what? Is 0,7 minus 0,5. Contact time. Contact time. 0,7 minus 0,5. So it means the contact time is 0,2 seconds. You understand? This is the contact time. This is the time the ball was in contact with the ground. With the ground. You understand, right? So the ball, it moved up and it took 0,5 seconds to return to its original ground. So it means we're going to say 0,5. That 0,5 we divide it by 2. You understand? Meaning that we're going to have 0,25. Is it 0,25 and yeah, we're going to have 0,5 divided by 2. 0,5 divided by 2. So that is the time that we are going to have here. 0,5 divided by 2. That's the time it took to reach its maximum height. Understand? Then here, from 0,7 to 0,9. From 0,7 to 0,9. The way we did the first one is not the way we're going to do the second one. Because this time is just continuous. Meaning that this is time 0 for this one. This is time 0. It was projected when it was 0,7 seconds. And then it returned back when it was 0,9. So it means 0,789. It means it took 0,3 to from its start until it reached its final velocity. It took only 0,3. Understand? So notice that we never say 0,9 will divide by 2. No. Unlike this one where we say 0,5 will divide by 2, we get the second for here. Understand? So notice that difference. Here we just count that when it's it started, it was 0.7. When it ended, it was 0.9. Meaning that the time it took from the initial to final, it is 0.3. From 0.7 to 0.9, it is only 0.3 seconds. So it took 0.3 seconds. So to reach its maximum height, it was 0.3 divided by 2. 0.3 divided by 2. You understand? That is to reach its maximum height. These are seconds. So if we were to draw a velocity time graph for this one, I'm going to give a very simple scenario. Here I wanted to show you how we calculate the contact time. The contact time, it is the space between the two, and I hope you saw how we deal with it. I want to draw the last velocity visit time graph, showing you maybe showing you 3 bounces, a ball bouncing 3 times, so that you understand. I hope you are moving with me. I hope you are moving with me.